Our digital world, from your bank account to government secrets, rests on a dangerous illusion. The assumption that complex math problems are simply impossible for computers to solve. For decades, that foundation held, secured by modern encryption like RSA. But now, a silent revolution is underway. Quantum computing leverages the bizarre laws of physics to process calculations simultaneously. Unlike any machine we know, a single quantum computer running Shor's algorithm can solve those impossible math problems in mere minutes. This isn't theory. This is a high-stakes countdown to Q-Day, the moment all current digital security is instantly rendered obsolete. We are in a global race against time to rebuild the entire foundation of the internet before the quantum world breaks it forever. This is the ultimate tech horror story, and it's already begun. The entire digital world, from your HTTPS web traffic to your secure email, rests on one simple, elegant idea. Encryption is just a math problem that's too hard to solve. The core of our security is built on something called a trapdoor function. Think of it as a door you can easily walk through in one direction. But to go backward, you need a secret key. Without the key, the journey backward is practically impossible. The two main security systems we trust, RSA and ECC, are built on different but equally formidable trapdoor problems. Understanding these problems is essential to grasping why a quantum computer is the ultimate threat. RSA is based on something you learned in grade school, multiplication. The process starts with two massive secret numbers, we'll call them P and Q. They are prime numbers, meaning they can only be divided by themselves in one. Multiplying them together is simple, and it creates one gigantic number, n. The entire world gets to see n. That's your public key. The trapdoor here is the calculation. Multiplying two numbers takes a millisecond. But working backward, trying to guess the original P and Q from the final product n is believed to be computationally impossible for normal computers. To factor a common 2048-bit RSA key, the fastest known classical algorithms will take longer than the age of the universe. That immense amount of time is why your bank account is safe. The second system, elliptic curve cryptography, or ECC, is newer and often used on mobile devices because it's more efficient. Its security is based on a problem called the discrete logarithm problem. Imagine a specific, complex curve on a graph. You start at a point G and you add G to itself a secret number of times, say K times, to get a final point Q. This is easy and fast for a computer to do. The world sees G and Q. The trapdoor is trying to work backward. Given G and Q, you have to figure out the secret number K. Because the mathematics of this curve is so intricate, a 256-bit ECC key offers the same security as a much larger 30,072-bit RSA key. These two systems, RSA and ECC, are the absolute cornerstones of modern digital life. They enable every secure conversation you have online. And for generations, the certainty that these problems are unbreakable has been absolute. But all of that confidence is about to be shattered by a technology that doesn't follow the rules of classical math. How quantum computers defeat classical encryption. The abstract mathematical threat of quantum computing became a tangible danger in 1994 when mathematician Peter Shor published a revolutionary formula, Shor's algorithm. This algorithm proved that a powerful enough quantum computer could solve both the integer factorization, RSA, and discrete logarithm, ECC, problems in polynomial time. For classical computers, the time required to solve these problems is dramatically longer, sub-exponential time, making them effectively impossible. Shor's algorithm effectively breaks the trapdoors of both RSA and ECC, instantly rendering them insecure for. The core genius of Shor's algorithm is that it transforms the original hard math problem into a seemingly unrelated but much easier one called period finding. The setup: classical reduction. The algorithm first mathematically transforms the factoring problem for RSA into finding the period of a specific function. This period R is the secret value that, once known, allows you to instantly find the prime factors of n using a simple calculation. The breakthrough: quantum subroutine. This is where the quantum computer steps in, designed specifically to find this period R exponentially faster than any classical method. A quantum computer uses two key techniques here: superposition and the quantum Fourier transform, QFT. Superposition allows a single quantum bit, qubit, to exist in multiple states at once, enabling the computer to evaluate the period function for many different values simultaneously. The QFT then acts like a super powerful filter. It transforms the quantum state so that when the qubits are measured, the output is highly likely to be a multiple of the necessary period R. This quantum advantage is what gives the algorithm its polynomial time complexity of O log n world, making it devastatingly potent. In response to this looming quantum threat, the world has launched the Post-Quantum Cryptography (PQC) race. The goal is simple: deploy quantum-resistant algorithms across the entire digital world before Q-Day. New math and NIST's cautious strategy, PQC abandons the math problem Shor's algorithm can solve, and instead relies on four new families of problems believed to be hard for quantum computers, with lattice-based cryptography emerging as the leading candidate. The U.S. National Institute of Standards and Technology, NIST, has led the standardization since 2016. In a key strategic move, NIST is ensuring cryptographic diversity by selecting both a primary algorithm, MLKM, and a code-based backup, HQC. This cautious diversification strategy mitigates the risk of an entire mathematical structure being unexpectedly broken. The transition is monumental because PQC algorithms come with significant trade-offs, primarily dramatically larger key and signature sizes. A Kyber public key is over 1,500 bytes, compared to a 64-byte ECDSA key. A dilithium signature can be over 4,000 bytes. These massive sizes challenge bandwidth-constrained environments like IoT devices and legacy systems. PQC algorithms are also often slower than their classical counterparts. Despite these issues, tech giants are moving forward, largely adopting hybrid approaches, combining classical and PQC algorithms as a transitional measure. This hedges against unknown vulnerabilities in the new schemes while providing immediate security. The race is truly on. It's between the speed of PQC implementation and the arrival of Q-Day. A chilling threat looms over data encrypted today. Harvest now, decrypt later, HNDL. HNDL is a strategy where adversaries steal and store massive amounts of encrypted data now, waiting to decrypt it once a quantum computer arrives. This makes data with a long security shelf life, like government secrets needing 50+ years of protection, an immediate target. The paradox is clear. The most effective quantum attack will be against data perfectly secure by today's standards. The consequences are staggering, potentially causing trillions of dollars in indirect losses. This threat demands immediate action. The U.S. government has set a hard deadline, mandating national security systems transition to quantum-resistant algorithms by 2030. The quantum threat is a bomb built in the future, threatening the past. We are in a two-front war, developing PQC and combating the covert harvesting of our present-day secrets. Success requires foresight and decisive action from every organization. The clock is ticking, and the stakes have never been higher.